Yeah, students, greetings of the day. This is your Ani Rao, faculty in physics from director of EAP classes. Okay, so today I have come with another topic known as work energy power. Okay, so now we'll try to throw some light on work energy and power. I would like to mention you that work in everyday actually life, the word which you use is different, and in terms of physics how you use its meaning is different. Okay, now sometimes as our exams are going on we can say that I am working very hard, sir. Okay, but as for physics the work done by you is zero. Okay, so in what context we can say work is done? So in physics we come across, okay, whenever some particular, for example, how you are defining the work. Okay, so whenever we have, for example, an object is there, okay, of mass some m, you can say, fine. So if you're applying some force on it, and if you cause some displacement in it, okay, so what you can say, some displacement s you have caused, so you're applying force in this way and direction of displacement is in this way, the angle between f and s is theta. So you can say in physics, whenever some force acts on a body and if it causes displacement, then only work is said to be done. So if there is no displacement, we can say work is not done. Okay, so definitely there has to be what? Some work done. So now here, whenever some force acts on a body and if it causes some displacement, then work is said to be done. And how it is displayed? Okay, how it is defined? That means whatever the force is acting, it is causing displacement, no? So take the force, how much acting in the direction of the displacement, okay, and multiply both of them. So force the direction of displacement, already we have discussed in components, isn't it? So F is the force acting and displacement is direction S bar. So what is the component of the force, the direction of displacement? So those who don't have idea of component, please go through my series vectors, you will understand there. In detail I have explained about how to resolve into components. Okay, so the component of force, the direction of displacement, right perpendicular, then this intercepting length becomes f cos theta. Therefore, the force, the direction of displacement is f cos theta. Therefore, into s displacement. So, therefore, work is defined as product of force and component of force, the direction of displacement. Or you can also take like this. So, force is acting like this and displacement vector is in this way. So not only force component direction of displacement, you can take displacement component also the direction of the force. So if you take displacement component direction of force, right perpendicular from displacement, so this intercepting length becomes now how much? S cos theta. This angle is theta. So you can say work is defined as product of force, okay, or displacement, okay, in the direction of force, as like this we have discussed. Or you can say force in the direction of displacement, that is f cos theta into displacement. This is one way of saying. Or take displacement in the direction of force, how much? S cos theta into f. So you can also say s cos theta into f. So both are same. F cos theta into s also fs cos theta. S cos theta into F also Fs cos theta. So in physics, whenever some force acts on a body and if it causes displacement, then work is said to be done and defined as the product of, okay, component of force, the direction of displacement into displacement, or component of displacement in the direction of force into force is defined as work done. Now we cannot say this much amount of work is done this direction. Okay, so we always say how much amount of work is done. So few amount of a certain amount of work is done, 10 joules, 20 joules, something. So we won't specify direction. Therefore work is here what? Scalar physical quantity. And coming for the SI unit, SI unit of work is equal to, as you are saying, the component of displacement, the direction of force into force, S cos into F or F cos into S. So this angle is cost value is having numerical value, no unit. So F is Newton and displacement is meter. This Newton meter is defined as joule. And if you come for here CGS unit of force, if you come across CGS unit is work is F into S. If you say N, force is what? Newton in SI system. CGS system unit is what? Dyne. And displacement is centimeter, dyne centimeter. So you can say 1 Newton meter is 1 joule. You can convert also here. Therefore 1 joule is 1 Newton meter. In laws of motion we have studied, students, 1 Newton value how much? 1 Newton value is 10 power 5 dynes into what? Centimeter. Yes or no? And here 1 meter is 100 centimeters, so you can say 10 power 2 centimeters. So 10 power 5 dyne, 1 Newton value, 1 meter is 10 power 2 centimeters, so you can say 10 power 7 dyne into centimeter. This is defined as 10 power 7 erg. Okay, so 1 joule is equal to how much? 1 joule is equal to 10 power 7 what? Erg. This is what? CGS unit of what? Force here. Okay. So now, CGS unit of your work done. So relation between CGS and SI unit is how much? So 1 Newton is equal to 1 Newton meter is 1 joule. So and 1 joule is equal to, you can call it as 10 power 7 erg. Okay, this is the relation between CGS and SI unit of what? Work. Now based on this particular value of theta, so how we define a work, okay, positive work, negative work, and all those things we'll talk here now. So as work is defined as, so F into S cos theta, or you can also write F cos theta into what? Yes. Okay, now here based on the value of theta, so whenever you are saying here, so some amount of force is acting on a body at some angle, causing some displacement over here. This is the direction of displacement. Angle between force vector and displacement vector is theta. Work done is this was a scalar quantity. Already in vectors we have studied Fs cos theta or F cos theta, both are equal to what? You can also say F bar dot S bar. So work is also defined as scalar product of force vector and displacement vector. Now, so first case we'll try to talk if theta is equal to 0 degrees, student. That means what? So force is acting on a body, okay, and causing displacement also in the same direction. So F bar vector and S bar vector, these both are pointing in the same direction, theta 0. So you can say W is equal to F into S into cos 0 degrees. Cos 0 value is 1. So simply F into S. So how much amount of force acting, and the applied force is causing displacement in the same direction. So you can say work done is equal to simply what, beta? F into S, simply product of the force and displacement. Okay. Now, so if theta value is changing here, for example, okay, so now theta value is, for example, 90 degree. If we take theta value, if theta is equal to 90 degrees, okay, how much amount of work, work done will be equal to F S cos 90. Cos 90 value is 0, so 0 work is done. Okay, so if theta is less than 90 acute angle, okay, you can take for any cos 30 degrees, 45 degrees, always will get positive work. Okay, work done will be here positive. And when theta is more than 90, how you can take, for example, if theta is equal to 120 degrees, okay, so work done will be F S cos 120 means 90 plus 30 I can write, so which is equal to F S cos of 90 plus theta is minus sin theta. Yes or no? So here cos, so minus cos of 90 plus theta is minus sin theta, that is minus sin 30. So here coming is sin 30 1 by 2. So of course here negative is coming. So work done is here a negative value. So work can be 0, work can be negative, work can be what? Positive. So like this you can say work can be positive, work can be negative, work can be what? 0. Like this we can define type of work. Okay. Now for example 0 work is already one more example I will try to give. For example, around the sun, for example, planets are revolving, or around the earth you can say moon is revolving. Okay, earth, moon is revolving in circular fashion, right? So what is the reason for why the actually moon revolving? Because of, everyone knows, because of what? Gravitational force. So instantaneous displacement of the earth is like this. Instant displacement of the moon is in this way, tangential direction. Force is radial direction. Angle between tangent and what? Angle between tangent and radius is 90 degrees. So work done by gravitational force in revolving the moon around the earth, how much? Gravitational force into displacement direction into what? Angle between them is cos 90. So 0 work is done. That's why the speed is not changing here. Speed is constant. Okay, so a very important question, previous competitive bit is this. Therefore work done by gravitational force in revolving the what? So can the moon or a planet around the sun, or you can say around the earth, here is 0 work done. Okay, so that's one example. Now work done, so positive already we have seen. So where negative work is done, for example, so you are throwing a ball on the ground, okay, with some velocity u beta. Okay, so what happens now? After some time the ball comes to rest, so the velocity becomes what here? 0. Why velocity become 0? If I ask the question, what will you say? Yes sir, this motion is being opposed by some tangential force which are opposing the relative motion of the ball with respect to the earth, will say. Yes or no? That is what friction we are calling. Now ball is undergoing displacement in the forward direction and friction is acting in the backward direction. The angle how much here? 180 degrees. Therefore work done by friction is equal to frictional force into displacement into angle between them how much? 180 degrees, so cos 180 is minus 1. So minus into F into S. What you are done here? This is work done by friction is here negative. Okay, is work done by friction always negative? Need not be. Sometimes friction what? So we also do some positive work. Okay, for example, already we have taken in the previous session when I am talking about friction. You are keeping some object on your hand, and when you are moving the hand, what is happening here? So along with your hand, the mobile or the object also moving. So who is making it to move? Friction is making it to move. So here friction is doing positive work. Okay, so friction may do negative or positive, it doesn't matter. So here we are talking about when work will be positive, when work will be negative, when work will be here 0. Okay, now for example, you want to lift an object, okay, from surface of the earth against gravity. Its mass is m. Okay, its mass is how much? M. So its weight how much will act, students? Mg downward. If I want to give some position with respect to ground, so some height h I want to lift it, how I have to apply force? I have to apply force in the upward direction. So here force is equal, minimum force required is equal to its weight, and displacement of the direction of the force, which is equal to h. So work done by applied force, work done by applied force will be equal to its weight, that is mg, displacement is h. So work done by applied force is here positive. But if I ask you what is the work done by gravity, student? So work done by gravity, when you are moving it by applying force, when you are moving it up, gravity is acting vertically downward, so equal to its weight. Gravitational force acting on a body is called its weight, and displacement is here how, students? Displacement is here upward, angle is here 180 degrees. So work done by gravity is what here? Gravitational force is downward, displacement is upward, so angle is 180, cos 180. So this will be minus mgh. So here work done by gravity is here negative, work done by applied force is here, applied force is here positive. Okay, like this, work can be positive, work can be negative, or work can be what? 0. So in physics context, whenever some force acts on a body and if it causes displacement in it, then only what you say? Work is said to be done. For example, you have a wall and you are continuously pushing it, but you could not displace it. What work done by applied force? 0. Why? Because you could not produce any displacement in it. So for example, vertical wall is there, you're applying large amount of force to push it here. Okay, hardly you can produce any displacement. Displacement is 0. So what is work done by applied force? Work done by applied force is 0, isn't it? So as you are not at all able to move it, no, so what happens? So no displacement, so no work is done. Okay, so like this you can apply context wise. Now sometimes you may give in vector form. Okay, so work done is equal to F bar dot S bar, result is a scalar. Okay, sometimes force vector will give displacement vector, just do dot product. Already we have done in vectors dot product. Okay, for example, some force acts on a body. So F bar is equal to I cap plus 2j cap plus 3k cap acts and causes displacements. Okay, so displacement vector, for example, it may go in coordinate form or direct vector form. Okay, cause a displacement of some, for example, 2i cap plus 0j cap plus 3k cap. What work done? Direct formula, work done is equal to some F bar dot S bar. Already we have seen dot product. So those who don't know dot product, please go to the series vectors dot product. Okay, two videos I made. Already half an hour one video, 1 hour, and one stretch entire vectors also have done. Go through those 3 series videos. Okay, you'll understand. Multiply simply coefficients. 1 into 2 is 2. Dot product A dot B. So 2 into 0 is 0, and 3 into 3 is 9. So this will be how much, students? That is 11 joule of work is done. So when vector form, force vector is given, displacement vector is given. Okay, this is what? So what do you mean by here? Work and types of work done. Next, coming for whatever the work we do, it appears as kinetic energy. Okay, that is called work energy theorem. So the statement is work done by all forces. Already we have seen all forces means vector sum of all forces. Vector sum of all forces means what? Net force. So where net force, work done by net force is equal to change in kinetic energy. So this theorem is called what theorem? Work energy theorem. You can prove it also. How, for example, you take a body of mass m. Okay, so initially it may be rest or move with some velocity. If you assume it is at rest, so if you are considering some force is acting on this body and causing displacement in it, so what you can say? So some s value displacement, and because of this application of force, some what displacement is there, therefore this work is being done on it. Some work is being done on it. So at the end of the displacement, say the body got velocity v. Okay, so how much amount of work is done by applied force? That is equal to force into displacement. Fine. So now, for example, in t seconds, it is causing this displacement. So you can say acceleration gain is equal to v minus u. U is, you can take u or 0 if it body starts from rest, divided by t. Yes or no? So now, and if you consider acceleration is constant here, and how much displacement? So you know, initial velocity, final velocity, acceleration is constant. By third equation, what you can write? By third equation, you can write v square minus u square is equal to as. Okay, you may take 0 or you may not take 0 also, students. If body starts from rest, you take 0. If body having some already some initial velocity, you can take not 0. Okay, so now fine. So from this you can understand that, so force value from Newton second lies m into a into s, right? So from here I can write a into s value. From this equation I can write a into s value as half into v square minus u square. You can assume this as 1, this as 2. So from 1 and 2, what you can conclude? Therefore, work done by applied force in causing some displacement, in giving some velocity to the body, okay, is equal to m into a into s. M into a into s value, how much we got? Half into v square minus u square. So you can say this is half m v square minus half m u square. Okay, this work done. So this is the work done. Okay, what? Applied force, or you can say only net force. Why? Because in vertical downward direction mg, upward normal, they are cancelling. Only force acting in the horizontal direction. So I can say work done with this applied force, okay, is coming as half mv square term minus half mu square. This is called final kinetic energy. We call it as final kinetic energy minus what? Initial kinetic energy. Therefore, work done by net force, we can call it as change in kinetic energy. Okay, what is kinetic energy? The energy possessed by a body by virtue of its motion. Here also one point you can think like this, student, differently. So as we mentioned that initial velocity is 0, no, whatever the work is done, how much amount of work is done now? If you consider 0, simply what? Half m v square. So we say this work done appears as energy, and this energy we call it as kinetic energy. Okay, so conclusion is that whenever some force acts on a body and causes displacement in it, then whatever the work is done by the applied force or net force, no, that is equal to change in kinetic energy. And this theorem is called what theorem? This theorem is called work energy theorem. Work done by all forces or work done by net force is equal to change in kinetic energy. Okay, yes, students. Now next you can see here. So keep in mind this statement. Okay, now kinetic energy is the energy possessed by a body by virtue of its motion. Just now we have seen, and indirectly we have derived the derivation also. Okay, expression for kinetic energy is given as half m v square, and it depends on what? Mass of the body as well as what? Velocity of the body. So if velocity doubles, what happens? Kinetic energy becomes. So kinetic energy formula is how much? Kinetic energy formula is here half m v square. By keeping mass of the body constant, if v dash is equal to v, what do you get? New kinetic energy will be, new kinetic energy will be half m into 2v whole square. It is 4 times half m v square. So kinetic energy become how many times, students? 4 times. And you can also write one more formula here, kinetic energy momentum relation also you can derive. So kinetic energy and momentum relation. So what is formula for kinetic energy? Kinetic energy formula is half m v square. You just multiply with m and divide with m, students. What will you get? 1 by 2m into m square v square. In laws of motion we have studied already. What is momentum? Mass into velocity. Therefore you can write down 1 by 2m into p square, since p is equal to product of mass and what? Product of mass and velocity. That is equal to what? Kinetic energy Ke is equal to p square by 2m. So here questions will be asked if momentum is increased by 10% or 11%. So what is percentage change in kinetic energy? Directly you can use this formula, kinetic energy momentum relation. So Ke proportional to what? P square. Or for a given body, if momentum is same, okay, if a body, for example, two bodies are there, okay, so both the bodies are getting same momentum, p1 is equal, p2 is equal, say p ankundam, okay, you can say assume, then momentum is same, then kinetic energy will be inversely proportional to mass. So focus on these points, we'll have numericals also. Okay, right, now coming for, This is what do you mean by actually work and what is kinetic energy. Now one more point, we talk about potential energy. So before I have done already, when you are lifting a body, okay, from the ground, for example, on the surface of the earth, you want to lift the body and you have to give some position, student. So when you are lifting, you are working against gravity. The gravity is acting vertically downward, mg, and you are giving displacement s is equal h. So work done by you against gravity, how much? Work done by you or us against gravity is, you're applying force vertically upward, displacement also upward, you're doing positive work, F into S, and that work how much you are doing? Mg into displacement is h, this is mgh. So whatever the work you have done in lifting the object from surface of the earth and giving some position, so this work done is stored as energy, and this energy is called what? Potential energy. And as you are doing work against gravity, this is called gravitational potential energy. So the work done by us itself is stored as energy, and this energy is called potential energy. You can have examples also, like for example, so bow, a bow of la drama, you can say. So when we stretch the bow, what happens? You are doing work in stretching it. That work done by you stored in the bow, okay, our arrow system, in the form of potential energy. When you release it, no, it appears in the form of kinetic energy. That is conservation of energy, we call. Understanding? So similarly, the energy stored in the dam, we call. So entire energy is stored in the dam in the form of potential energy. When you open the gates, so what happens? Water is rushing out with large amount of energy. That energy is kinetic energy. From where it is coming? Potential energy converts into kinetic energy. Okay, so like some movies we see, so a big boulder is rolling down a big hillock, isn't it? So at when it is on the hillock, it has potential energy. When it rolls down and it creates massive destruction, no. So from where it is getting energy? The energy, hidden form of energy, potential energy, converting into what? Kinetic energy. Okay, that's what we have seen. Gravitational potential energy is equal to mgh. One more example also, again, spring energy. So spring energy, you can see, student, for example, I have a spring. So I connect a block attached to this one like this. So when I stretch the spring, what happens? Spring force develops in it, that is equal to kx. So initially no extension. When initially no extension, extension is equal to 0. So force also 0. So when I cause some displacement s or x in the direction, so force also develops here, that is equal to kx. So initial force is 0, final force how much here now? Kx. Okay, so average force exerted by the spring force, average force by spring, you can say, or we are doing work in stretching the spring, right? So average force exerted by us is equal to 0 plus kx by 2, you can say, simply kx by 2. Okay, therefore the work done, so work done how much now here? Work done how much? Therefore the work done by the applied force is equal to the average force exerted into displacement, that is kx by 2 into x, which is equal to half kx square. In a higher class, the same thing we derive by the method of integration, students. Okay, for small amount of displacement like this we do. Okay, don't worry, we'll learn all those things. So k spring constant, if you pull it the bob the small distance x, okay, so small amount of force you are applying F. Okay, so the work done by small amount of force dw is equal to F into small displacement, you can call as dx. So total work done we say after learning integration, so total work done integration dx we call. So your work done is equal to applied force must be equal to spring force kx into dx. So from here k constant, x value, integration of x dx we call as x square by 2. You don't worry here, that's why something whenever varies linearly, no, so we take average force as initial plus final by 2. Okay, 0 plus kx by 2, that is kx by 2 average force exerted, and displacement x, so half kx square. Okay, this we learn in 11th and 12th we learn. So as I am making both foundation level to JE level, no, so I will discuss in numericals also those kind of things. Now currently you can say whenever variable force acts, okay, whenever variable force acts, we use the method of what? Integration for what? Doing the numericals, integration f dx. Okay, so and normally you can say simply what happens? Normal constant force means f dot s. Okay, so variable force means always remember integration f dx, that is half kx square. So this particular work done in stretching the spring or stretching the bow, we'll say, no, so stored as energy, okay, there, that is called potential energy is equal to half kx square. Okay, so we have here, so we define potential energy for this kind of forces. Okay, for example, here if we stretch the spring from already initial position xi to final position xf, we say the work done is equal to, we say, change in potential energy, that is equal to half kx final minus half kx initial. we call it as half k into final displacement minus initial displacement. So here when the spring is already having some initial position xi, again you are stretching it to final position xf from natural length. So natural length already initial extension, now final extension, so work done, okay, nothing but change in potential energy. So here if initial position is final position, so work done will be equal to 0. That means you are stretching some initial value, again you are bringing it to what, same value. So initial position, final position, when they coincide, the work done, okay, in stretching again bringing back, we can call it as a loop. Okay, the work done in a loop, if it is equal to 0, that kind of force is called conservative force. Okay, so here, so spring force you can say, or gravitational force you can say, okay, spring force, gravitational force, all of they are called here conservative forces. Okay, so what are conservative forces means? Conservative force means if the work done by a force, if the work done by a force in a closed path is equal to 0, it is called conservative. One more example I will give you. Say you are lifting a block in a gravitational field from here to here, like this you are lifted, again you have brought, okay, down here, again you have brought back to initial position. Say this is A, this is B, this is C, this is D. Can you tell me in this ABCDA loop how much amount of work is done by gravity? So say this is H displacement, okay, this is some X, again this is H, this is again X. So from work done from A to B, work done by gravity I am talking. Okay, you know, lifting it, okay, gravity is acting downward, displacement is upward, negative work done, so minus mg into H. Now work done from B to C. When you are going from B to C, gravity acting downward, displacement is horizontal, angle is 90. Just now we have seen work done is equal to 0 when angle is 90. Next, from C to D. So gravity also acting downward, displacement also downward, theta is equal to 0 degrees. So work done how much? So simply work done from C to D is mg into H, that is equal to mgh. Now again we talk D to A. When you are carrying the block from D to A, gravity will act vertically downward, displacement is horizontal, angle is 90. So work done from D to A will be 0. If you add all these work done, total work done in loop, add minus mgh plus 0 plus mgh plus 0. What happens? This all get cancelled. So work done in a closed loop is equal to 0. That's why this kind of force says if the work done by a particular force in a closed path is equal to 0, such kind of forces are called conservative force. So under this heading, spring force is falling, as well as what? Gravitational force also falling. So in second year we learn in electrostatics also, electric force also conservative force. Okay, right, this is about what do you mean by work, what is kinetic energy we have defined, what is potential energy, gravitational potential energy, and spring energy. Okay, so once you revise this particular video and go through it once. Okay students, right, next we are talking about conservation of mechanical energy. Already you have learned energy can neither be created nor destroyed, total energy of the system always remains the same. Simple example you can say here, sum of potential plus kinetic energy constant. Okay, so for example, so from the ground certain heights you are releasing a block, and here condition C, mechanical energy to be conservative. Okay, mechanical energy to conserve, the forces acting must be conservative in nature. What nature? Conservative in nature. That means the forces like gravitational force, spring force, electrostatic force must only act. So whenever a body is only under the action of conservative forces, then only total mechanical energy is conserved. You should keep in mind this one. Okay, if not, what happens? So you saw what happens if other forces are acting, then what happens? No, the work done will be equal to change in mechanical energy. So if conservative force acts, change in mechanical energy becomes equal to 0, means mechanical energy becomes constant. So if not, what happens, sir? Means if conservative force are not acting, then what happens? When conservative force are not acting, then work done is equal to change in mechanical energy. Okay, so now here, say for example, a body is released under the influence of gravity. So point A you can say, okay, so it comes to point B and reaching the ground point C. Say you can say it as before reaching ground, as you are releasing it, no, say travel x distance traveled. Okay, so total height, for example, this is capital H. So if I consider potential energy at A, how much? So potential energy at A, how much means simply what the formula I give, mgh. H is what? Height from what? Ground, reference level you can say. Now, so this is mg and height from the ground is h, that is mgh. So as we are releasing, so initial velocity is 0. Initial velocity is 0. So what is kinetic energy at A? Kinetic energy at A is equal to 0. So therefore total mechanical energy. Mechanical energy means sum of potential and kinetic energy. Keep in mind. Okay. So sum of potential energy and kinetic energy is called what? Mechanical energy. So we are talking about conservation means what? It remains the same. We are going to prove it now. So by a simple example like freely falling body I am taking. Okay. So let us consider the case of a body which is released from certain height. At point A, height is h. Therefore, height is h means total potential energy is mgh. As we are releasing means velocity is 0. So kinetic energy is 0. So total mechanical energy, sum of potential energy plus kinetic energy. mgh plus 0, how much students? That is mgh, equation number 1. Okay, now so when body reaches to point B by traveling x distance, so let's say its velocity on reaching is vb. How much velocity on reaching any point from certain height? Already we did it in kinematics relation. Velocity on reaching certain height after traveling certain distance is root 2gx. Yes or no? You can see kinematics my series I derived over there. Okay, so velocity on reaching or velocity reaching ground also root 2gh from height. From x height means root 2gx. So what is the kinetic energy on reaching B, students? That is equal to half mvb square, which is equal to half mvb square is root 2gx whole square. We can cancel over here and we'll get half into m into 2gx. 2 get cancelled, student, mgx. So kinetic energy on reaching point B. Kinetic energy on reaching point B, how much? Kinetic energy on reaching point B is equal to how much? That is equal to mgx. Okay, now as it is reaching here, its height from the ground will be how much? H minus x. Why? Total height is h. Okay, x distance traveled, so remaining is h minus x. So what is the potential energy at B? Is equal to mg. Height from the reference level is h minus x. Okay, so you can now, therefore total mechanical energy at B will be potential energy at B plus kinetic energy at B. Potential, expand this bracket, student. So this is equal to mgh minus mgx. So plus kinetic energy already we have derived as mgx. So this to get cancelled. So we have mgh. So at A also total. At A also total mechanical energy is mgh. At B also we have total mechanical energy. At B also we have what? Mgh. Okay. You can also on C also you can say on reaching ground. And reaching ground you can also write, students, here on reaching ground height from ground is 0, so potential energy at C will be 0. Do you agree with me? Yeah. And when the body reaching from that height on reaching C, velocity on reaching C, height formula is what? Root 2gh. H means capital H. Therefore kinetic energy on reaching C will be half m into vc square. So half m into square this vc root 2gh. Root 2gh whole square is 2gh. So we'll have how much? mgh. Therefore total mechanical energy at C is potential energy is 0, kinetic energy is mgh. So total becomes how much, student? mgh. Therefore, so in case of freely falling body we have proved that so total mechanical energy at A, at B and at C is also equal to how much? Equal to mgh. So you can say so mechanical energy at A is equal to mechanical energy at B is equal to at C. So whenever the forces acting on a particle or a system, okay, only conservative in nature, okay, like gravitational force, okay, spring force, electrostatic force, the total mechanical energy always remains the same. So you have seen here when you're releasing a ball or kind of ball, something object you're releasing, okay, what is happening here? So its height decreasing means potential energy is decreasing, kinetic energy is increasing. So potential energy converting into kinetic energy. This is what? Conservation of what? Mechanical energy in case of freely falling body. Similarly, we can also prove in case of spring block system also. Okay, so or a simple pendulum also you can prove conservation of mechanical energy. Okay, when the bob is oscillating, so when it's going A to B, okay, again B to A, again this side C. So when it's going oscillating, no, A to B, against gravity going, velocity decreases, becomes 0 here, kinetic energy is 0, again coming down. Okay, so whatever height increasing means potential energy increasing, velocity decreasing means kinetic energy is decreasing, kinetic energy decreasing, potential energy increasing. After going extreme position it comes down. What happens now here? Again velocity becomes maximum. Again when it goes left side, again height increasing, potential energy increases, kinetic energy decreases. So kinetic energy is 0 at extreme positions, Okay, but potential energy is maximum. Potential energy is maximum at extreme positions. Okay, and kinetic energy is maximum at mean position. You can draw all the graph also here. So kinetic energy formula and all. Okay, with velocity half mv square, position also. So you can find out these graphs also in numerical wise. So potential energy, kinetic energy, always they are interconvertible. Okay, so curve it will be a, so potential position if you draw the graph. Okay, spring block you can talk, or you can say simple pendulum also you can prove it. In oscillations in detail I will do. Now currently you can also consider potential energy of spring block system also, like half k x square we have seen. If you draw the graph for potential energy versus displacement is a curve, quadratic equation. Okay, so if you consider spring block system also, if you pull it aside and leave it, no, from x is equal to 0, when you pull it, so about this position it will go maximum, this right side will go, again comes to mean position, again goes this side beta. So you can say this is right side plus a, you can say minus a maximum displacement. So when it's going here, velocity becoming 0, but extension is maximum, so potential energy is maximum. When it comes to mean position, velocity is maximum, so kinetic energy is maximum and potential energy is minimum. When again going left side, no, here kinetic energy is 0, potential energy is maximum. So here now at x is equal to 0, potential energy is 0. When x is equal to plus a, potential energy is maximum. Potential is maximum. X is equal to minus a, also potential energy is maximum. Okay, if talk kinetic energy reverse, this is graph for potential energy. If at kinetic energy if I talk, so at x is equal to a, velocity is 0, so kinetic energy is here 0. Kinetic energy is 0. When x is equal to 0 means mean position coming with maximum velocity, so kinetic energy is maximum here. And when it comes to x is equal to minus a, kinetic energy is again 0 here. Okay, sorry, kinetic energy is maximum means 0 here at extreme position. So you can draw the graph like this. Okay, so this is kinetic energy graph. This graph also important, JEE so many times it is asked. Okay, so in foundation level also it will be memorable thing. Okay, right, so this is what potential energy and kinetic energy. Next last topic now we talk about work energy. I am talking just synopsis in a brief view. Okay, and we'll take numericals also soon based on the basic definition whatever I have done. Okay, now power. So who is powerful? The person who has capacity of doing more work is more powerful. So ability of doing work is measured in terms of power, students. Say same question paper is given for two students, so whose ability is who does in lesser amount of time. Now we talk about power. So as I mentioned, the rate of doing work is called what? Power. The person, so who takes, see, same amount of work is being done by two person, but the one who is doing in a lesser amount of time, we say more amount of power. Okay, so power is inversely proportional to times and defined as rate of doing work. What's a rate of doing work? So you can say average power means total work done by total time taken, and we defined instantaneous at an instant of time. So small amount of work done in small amount of time dt. So you can call dw by dt is instantaneous power, and total work done by total time taken is called what? Average power. So you can also write this one as d by dt of work done is defined as f dot s. Yes or no? So you can say f is constant into, you can simply write as ds by dt. The rate of change of displacement is called velocity, so you can also call f dot v. So power is also defined as scalar product of force vector and velocity vector. Force vector and what vector? Velocity vector. So power is also a scalar quantity. So rate of doing work is called what? Power. So like power of the engine we say, so how much amount of work is done in given time, that is called power of the engine. Okay, we can call efficiency, how much amount of work is done, how much amount of energy the engine being absorbed. Okay, work done by energy absorbed can be called as efficiency. Percentage means multiply with 100. Okay, such kind of numericals also we'll be seeing. Okay, now coming for, so one to basic numericals we'll be taking here now. A block of mass 2 kg is there, moving with a velocity of how much? 3 meter per second. So what is kinetic energy right formula, students? Kinetic energy is equal to half mv square. So half mass how much? 2 kg, velocity is 3 square, simply 9 joules of work is being done. Okay, now box rides from a height of how much? 5 meter height. So what you can write, what is the velocity and reaching ground? So simply says the smooth surface you can take a block of mass some m, okay, sliding from a height of 5 meter, when reaches the ground, so here potential energy is mgh, converts into what? Kinetic energy. So by law of conservation of mechanical energy you can write potential energy converts into kinetic energy. Okay, so V square will be equal to 2gh. So V how much? Root 2gh, velocity on reaching ground, student. Okay, you should understand here, when a surface is here smooth, okay, from which point we are releasing, so only vertical displacement matters here. If body is simply released independent of path, depends only on what? Vertical displacement, velocity and reaching ground. Okay, now you can substitute here, we'll get the answer. Now that is what 10 meter per second energy method we have done. Fine, this is how work and energy, and next class I will take based on the numericals. Okay, so soon I will be uploading that video also. So hope you understand what exactly work means. Capacity of doing work is called what? Energy. So energy is measured in terms of work done. The more work done, more is the energy involved. So, and hence energy and work are having same units, and that is what here SI unit is joule, and CGS unit is what? Erg. Already we have seen 1 joule is equal to 10 power 7 erg, student. Okay, yeah. So, and conservation of mechanical energy, and all those points I have discussed, just work, energy and power. So capacity of doing work is called energy. The rate at which work done is called what? Power. Therefore work done by time taken is called what? Power. Okay, just remember these brief things, and we'll come up with a few more numericals in upcoming session. Okay, thank you all. So please subscribe and share among all of your friends. Okay, my channel. Yeah, thank you all.